Now, this is a sample problem of Newton's laws of second motion, wherein we're going to apply calculus since we have an unknown variable v squared. Now, a 10-kilogram mortar shell is fired vertically upward from the ground with an initial velocity of 50 meters per second. Determine the maximum height it will travel if the atmospheric resistance is measured as drag force. So since this is a resistance, we're going to use drag force, Fd, is equal to 0.01 v squared newtons, where v is the speed at any time or any instance. Now we are given with the mass of the mortar shell, m is equal to 10 kilograms. The initial velocity is at 50 meters per second. And then we have the equation, quadratic equation, as drag force is equal to 0.01 v squared newtons. Now we have the unknown, which is the required to be solved in this problem, the height. Okay? Maximum height, y. Now, why are we going to use the variable y? Because the mortar shell is fired vertically upwards. So we're going to use variable y for the maximum height. Now, let's proceed with this solution. We are given with a mortar shell, which is fired vertically upwards. As you can see here, a soldier firing a mortar shell upwards. Now, if we're going to consider the free body diagram of this shell, okay, as a dot here. Now we have the drag force and the weight pointing downwards. The drag force is actually the air resistance. So since this is air resistance and the mortar shell is fired upwards, now the drag force will be pointing downwards along with the weight of the mortar shell. Initially, the height y0 is equal to 0 and the initial velocity 50 meters per second. So at this point, this height, okay, y is equal to 0. And then once the soldier starting firing it, our initial velocity becomes 5 or 50 meters per second. At the maximum height, y is equal to h. The velocity, since this is free fall, would be equal to 0. The free body diagram shows FBD to act downwards, or we have the FG, the drag force acting downwards since this is resistance, because it slows the upward motion of the mortar shell up until it falls down. Thus, we can write the following as the summation of force y component, since all the forces we're going to consider is upwards and downwards. So summation of Fy is equal to mass times acceleration with the vertical axis AY. Now let's substitute the following. So since the forces are pointing downwards, we're going to use negative. The summation of forces Fy now is equal to negative drag force minus the weight of the mortar shell. Now, why is it negative? Or why are these forces negative? Because downwards, okay? So this is negative Fd plus negative W, or Fd, negative Fd minus W is equal to mass times acceleration with respect to the vertical axis AY. Now, substituting the following values, since we are given with the drag force with quadratic equation. So this is negative 0.01 v squared minus 98. Now, how did we get the weight of the mortar shell? So since our mass is 10 kilograms multiplied with the gravitational acceleration of Earth 9.8 meters per second, this gives us the weight at 98 newtons is equal to 10 kilograms multiplied with our unknown acceleration for the vertical axis as a, or ay. Now, the acceleration depends on v and is therefore variable. Since Remember, we have the acceleration as the function of velocity v. We can relate a to v using the rearrangement described above. Now we are going to use this equation. Now remember, acceleration with the derivative of the distance s is equal to velocity multiplied with derivative of velocity dv. Now, we're going to replace ds with dy since we are dealing with vertical direction, okay? This becomes a dy v dv, okay? So let's substitute our acceleration here, okay? A. Now, before we get a here, we need to divide both sides of equation with 10, okay, to eliminate 10. To bring out a. Now this becomes negative 0.001 v squared minus 9.8, okay, multiplied with the y is equal to velocity multiplied with the derivative of velocity dv. Now, if we're going to divide both sides of equation with negative 0.001 v squared minus 9.8, this gives us with the following as dy is equal to v dv all over negative 0.01 v squared minus 9.8. Now, our limit for the dy, since this is height, and we are required to determine the maximum height h, okay, or y, but since this solution provides us h as an unknown variable as well, so we're going to start from 0 up to our upper limit unknown variable h is equal to the limits for the velocity v dv all over negative 0.001 v squared minus 9.8. Okay? The lower limits at height equal to 0. Once the soldiers started firing the mortar shell, okay, this is 50 meters per second with 0 as our upper limit. Why is it 0? Once the mortar shell reaches the maximum height, the velocity at the maximum height is equal to 0 and it will start to free fall. All right. Now, this gives us h equal to negative 50 as our lower limits, or the integral of 50 lower limits and upper limits of 0 with the following equation as v dv, or velocity derivative of velocity all over negative 0.001 velocity squared plus 9.8. Now, if we're going to simplify this, this gives us, okay, the natural logarithm law. So our constant here is negative 5 times 10 raised to 3. The natural logarithm of 0.001 v squared plus 9.8 with our limits to be substituted on the following equation as lower limit 50 meters per second and our limit as 0. Okay. This gives us the height h or y, the maximum height 114 meters as our final answer.